Hello, everyone. Welcome back. So far, what we've seen is that overfitting is very bad. And therefore, if your model has a complexity parameter, you picking the right complexity parameter is very important. If your model complexity parameter is too low, it will not be flexible enough to understand the complexity of the data. But if it's too high, it'll be overfit and it'll just be terrible. It'll work great on the training set, sorry, but it will do nothing good on the testing set. So we need to find the Goldilocks zone. We need to find the happy middle. And in this video, we're going to learn about a very powerful tool for finding this. Name of this tool is cross-validation. So we're going to get to that in a little bit, but first let's do some of our standard importing and pre-processing. So I want pandas. Import pandas as PD. Import numpy as np. From matplotlib, import pyplot as plt. Okay, now we also need to get the data. Make sure you got the Titanic CSV in the same folder as this one. pd.read CSV Titanic.csv. And in case you need a reminder, the Titanic data set looks like this. Titan. Wait. Oh, yes, forgot to assign it to the name Titanic. There we go. All right, so we got a list of people. Some of them survived the Titanic, some of them did not. We got their age, their gender, etc. So now, once again, we are going to use train test split to divide our data in two. So we're going to do this the same way as before, which is going to say from sklearn.model selection, import train test split, np.random seed 1, 2, 3, 4, train test equal train test split Titanic. And this time let's go with a test size of equal to 0.2. So this looks like nearly the exact same code as before, and it is, but here we're going to be using the test set for a different purpose. We're not going to be using it to tune our parameters. And this encodes a very important difference, which is that when you're doing it for real, you should never do anything with your test set until the very, very, very end. Because you want to have the test set as an honest indicator of how good your model is. And it cannot be corrupted. It needs to stay pure. And then you don't touch it till the very end when you're actually performing your test. It's like if you're studying for a test in school, you're not allowed to see what answers are going to be on the test ahead of time. Okay, so we're also going to prep the data sets, and in a very slight cheat, we're going to prep both the training and the test sets all at once, because we've decided this is not something we're training or tuning. So this is a very, very benign cheat but in principle, this line here shouldn't appear till the very end. But for teaching purposes, I'm just going to get it out of the way once, because it's not actually going to be cheating in a way that actually helps us. Okay, so that's our pre-processing. We've got it all out of the way, even the part that we probably shouldn't have. And now we're getting to create k-fold cross-validation, which is the main point of this video. So the idea is we take our training data, all of our data, we split it into training data and test data. And now we're just going to look at our training data, because we're not going to do the test data stuff till the very end. And we're going to split the training data into 5 folds: fold 1, fold 2, fold 3, fold 4, fold 5. And what we're going to do is we're going to select fold 1, train the model on 2, 3, 4, and 5, and then test on fold 1. And see which parameters work best. But then we're also going to make fold 2 be like the mini test set and train the model on 1, 3, 4, and 5. And also with fold 3 as the mini test set, etc. And so for any given choice of parameters, you can test it on 5 little mini tests, and you can then get like some sort of guess of how accurate your model is going to be. And what you do is you select the parameters which, based on this averaging procedure, seem to work the best. But you don't actually train on the test set until after you've selected your parameters. So this is a bit complicated, but the good news is that the people at scikit-learn have already done a lot of pre-written functions that will make this a little bit easy, or relatively straightforward to code up. So we need to, from sklearn.model selection, import cross validation score, and we're also going to get a tree. T is equal to tree.decision tree classifier. And in our first round, let's just set the max depth equal to 3, so that way I can show you how cross-validation works. We're eventually going to select the best depth, but we'll get to that in a little bit. Alrighty, so now I say CV scores is equal to cross-val score T X train Y train number of folds CV equal to 5. And let's take a look at what pops out. So we get 5 numbers. So these are 5 numbers that were all of us training a model with the max depth equal to 3. And these 5 numbers correspond to the 5 rows in this picture, where the first one is that fold 1 was the validation set, and then fold 2 was the validation set, then fold 3 was the validation set, etc. Now really what we care about is the mean. So let's take a look at the mean. And okay, so that's our average cross-validation score. And heuristically, we can guess that if we used 3 as our maximum depth, that this is probably about what we would get on the test set. We can't know for sure, but this is our reasonable guess. All right. So now what we're going to do is we're going to loop over the possible depths and find the best depth. So to do this, I'm going to let n be our largest depth and set that equal to 30. I'm going to create an array of scores. Scores is equal to np zeros, length n. For d in range 1 to n plus 1, so it's going to go from 1 to n. We're going to set a new tree. With max depth equal to d. And then scores, the d minus first entry, because scores is going to start at 0, but depth starts at 1. So we need the minus 1. Is going to be cross-val score, t x train, y train, cv equal to 5, dot mean. Alrighty. And now we say if scores d minus 1 is better than the best score, then we're going to perform our update. And we also need to initialize up best score to start off at the best score being negative infinity. All right. So then best, if we do the updating, best score becomes scores d minus 1. And best depth becomes equal to d. All right, so let's see what the best depth is. and what the best score is. Okay, it says the best depth is 5 and the best score is 81.5, which if we scroll up, that was just a little bit better than what we got with the depth of 3. And now let's look at how this kind of varies from one depth to the other. So we could do fig x equals plt.subplots 1, x.scatter, np.arrange 1 plus 31 versus scores. And here's something nifty we're going to do is we're going to make the title equal to best depth plus best depth. But best depth has to be a string, so let's convert it to a string. And so what we see is that the best depth is 5. 1, 2, 3, 4, 5. It seems that and it looks like 3 was actually also pretty darn good. And clearly once we get past, what's it, 1, 2, 3, 4, 5, 6, 7, 8. Once we get up to 9, we're very clearly starting to overfit and things just get worse from there. So now we have some sort of reasonable estimation that the best depth is probably 5. So now we can test this out on the test set. And really, if we were being truly honest, I do want to highlight this does not make any difference. What we really should have done, this line right here actually should have not been done till all the way down here. It makes no difference because we didn't actually do anything with the information from the test set, but really we should have just left the test set completely untouched if we were being 100% honest. Okay, so now let's test it out. We're going to say T equals tree dot decision tree classifier max depth equal best depth T dot fit x train y train, and then our score is going to be our score on the test sets. 84.2. Awesome. That's way better than we did before. We actually got even better than we did via cross-validation. That's not always the case, but sometimes you get lucky. So now we have all of the main big picture ideas for how the workflow goes. So you separate out your test data from your train data. You clean and prep your data, and you want to clean and prep them separately. In theory, you shouldn't even prep your test data till the end, although it's acceptable to slightly cheat if you know in advance what your prep is going to look like and you're not like learning the prep from the data. Then we identify a set of candidate models, i.e. just different types of decision trees. We use validation to estimate how the model will perform, and we select the best model. And then finally, score the best model against the test set and report its results. This is the basic flow of machine learning. There's more to data science, but as far as machine learning goes, this really is the principal idea of the big idea. All right, that's it for this time. I'll see you again next time.